In this video, we will practice solving optimization problems. That's where we find the input value that leads to a desired output value. The second problem is a rate-in, rate-out problem from a past AP exam. If you appreciate the content, please give it a like. Number 22. A rectangle is bounded by the x and y axes and the graph of y equals 6 minus x over 2. What length and width should the rectangle have so that its area is a maximum? In other words, as the point x, y moves along this line, what are the coordinates where the rectangle has maximum area? An optimization problem involves a secondary equation, which in this case they just gave us, and a primary equation, which represents the quantity you are trying to optimize. In this case, we are trying to find the maximum area, so the primary equation will be an area equation. You make up your own letter here for an optimization problem. We're going to use A for area. The area of this rectangle is base times height, so that's going to be x times y. The primary equation must be rewritten in terms of a single variable. That's where the secondary equation comes in. Let's use the expression y is equal to this to substitute for y in the area expression. Let's go ahead and view this x as x over 1 and distribute. I'm going to rewrite this using the a plus b over c rule, which says we can rewrite an expression like this as a over c plus b over c. In my mind, I'm thinking this, but I'm going to erase this in a moment. Instead of 6x over 2, I'm going to put 3x. And instead of x squared over 2, I'm going to put 1/2 x. Did I say 1/2 x? I meant 1/2 x squared. Now we can find a prime, taking the derivative of each term. The derivative of 3x is 3. And here comes the power rule. The 2 comes to the front. 2 times 1/2 is 1. So we just have negative 1, negative 1x. So, okay, that's really simple. A prime is 3 minus x. To make the A prime sign chart that we're heading for, we need to find where A prime is equal to 0. Setting this equal to 0, we get x equals 3, our one critical value. Simplest A prime sign chart ever. Be sure to include 0 as the lower limit of this domain because the rectangle is bounded by the x and y axes, so x cannot be less than 0. It can't be equal to 0 either, or we wouldn't have a rectangle. We need to decide whether 3 minus x is positive or negative in each interval. 3 minus x is equal to 0 right at x equals 3. For values of x between 0 and 3, that would be like 1, for example. Obviously, 3 minus 1 is a positive. Anything bigger than 3, and you're going to get a negative number, like 3 minus 4 is negative 1. Normally, we would say A has a relative max at x equals 3 because A prime changes from positive to negative. However, relative max is not good enough. We need to find the absolute maximum area. Luckily, this is a special case where A only has one critical value on its entire domain. This single critical value divides the domain into only 2 intervals. Since we know that A prime is positive for the first portion of the domain, then we know that the area A is increasing over the first portion of the domain. And since A prime is negative for the rest of the domain, that means A itself is decreasing for the rest of the domain. This means A has an absolute maximum at x equals 3, not merely a relative maximum, since we have accounted for the entire domain. We say A has an absolute maximum at x equals 3 because A prime is positive on the interval from 0 to 3, and A prime is negative on the interval from 3 to infinity. Be sure not to say it's because A prime changes from positive to negative. That only gives us a relative maximum, not the absolute maximum we need. Ha! I just noticed they gave away the answer in the picture. Anyway, we found the x-coordinate that maximizes the area. We need to find the y-coordinate that goes with it. At x equals 3, y is equal to 3 over 2. Be sure to answer the actual question with your closing statement. We were supposed to find the length and width that maximize the area of the rectangle. So we say the length and width that maximize the area of the rectangle are length equals 3 and width equals 3 over 2. Number 24 is calculator active. There's a common type of FRQ on the AP exam that I think of as a rate in, rate out problem. We will see these a lot more second semester, but you might as well get used to them now. Fish enter a lake at a rate modeled by the function e, given by e of t equals 20 plus 15 sine pi t over 6. Fish leave the lake at a rate modeled by the function L. L is equal to 4 plus 2 to the 0.1 t squared. Both e of t and L of t are measured in fish per hour, and t is measured in hours since midnight, t equals 0. At what time t on the interval from 0 to 8 is the greatest number of fish in the lake? Justify your answer. Notice that we are asked to maximize the number of fish in the lake. However, nowhere in the problem did they name a function that represents the number of fish in the lake. You don't actually need a named function for the number of fish in the lake, but I'm going to temporarily make one up because that's what you're comfortable with. At the end, I'll go back and show you how to write the answer without making up a new function. But for now, let's let f of t represent the number of fish in the lake at time t. In that case, f prime would represent the rate of change in the number of fish in the lake at time t. Now here's the key. On a rate in, rate out problem, the overall rate of change is given by the rate in minus the rate out. Since fish enter the lake at a rate given by e of t, and fish leave the lake at a rate given by L of t, the overall rate of change of the number of fish in the lake is given by e of t minus L of t, the rate in minus the rate out. By the way, when they define a function for you in the setup of the problem, in your work, you don't have to recopy this whole expression. You can just name the function like this. Now is the time that we would normally make an f prime sign chart, and we would use that to find the input value that optimizes the output value. On a calculator active problem, we graph f prime, and the graph is the f prime sign chart. Take out your TI-84. Let's type in e of t as y1 and L of t as y2. Always reset your calculator at the beginning of an FRQ by hitting second plus 7, 1, 2. That gives you a fresh calculator. You can make a nice vertical fraction by hitting alpha x. The rate in e of t should look like this, and your rate out L of t should look like this. Drop down to y5 and put 0. This will graph the x-axis itself, which will make it easy to find the zeros of the function later. Now let's type the equation for f prime into the calculator. That's e of t minus L of t, which will be y1 minus y2. I'm going to put this f prime rate of change equation on y4. I just like the color. I'm skipping y3 because it's black and it will be harder to see. So we need y1 minus y2 right here. You can make y1 show up by hitting alpha, trace, enter. And we want y1 minus y2. So we'll do alpha, trace, 2. So this is f prime. Remember, our goal is to graph f prime, which will act as our f prime sign chart. But right now, we are also graphing y1 and y2. So let's turn these equations off. So you can go over to the equal line, and if you hit enter, see how this is highlighted right now? If I hit enter, it's not highlighted anymore. So when I graph, it will only graph the equations where the equal signs are highlighted. So let's turn off the graph of y1 by hitting enter. So when we hit graph later, it will only graph f prime and the x-axis. Before we graph, let's adjust the window based on the domain, which is from 0 to 8. So hit the window button, and we will let x min be 0, and x max will be 8. Let's go ahead and hit graph and see what we've got so far. We can always come back and adjust the y min, y max later. Okay, so we can see the intersection point, but it looks like y max needs to be bigger than this. So let's go back to window, and let's adjust y max to be 50. And you know what, let's keep the balance and call y min negative 50. Perfect. We can use the graph of f of t as an f prime sign chart. There is a critical value here, which we will find in a moment. But we can tell that f prime is positive to the left of this critical value. It's above the x-axis, and negative to the right. Here's why I had us graph the x-axis itself. You can see it here in green. We can find the critical value by finding the intersection point between f prime and the x-axis. So we can hit second trace and choose 5 for intersect. Move the pointer close to the point of intersection and hit enter 3 times. Enter, enter, enter. Kabam! 6.2035. The College Board will accept 3 decimal places. However, we have found that students will often try to round to 3 decimal places and they round wrong and they wind up losing the point. So the solution is always use 4 decimal places and never try to round. Normally, we look at an f prime sign chart and do the first derivative test, and we say f has a relative max at x equals 6.2035 because f prime changes from positive to negative. However, a relative max is not good enough. We need the absolute maximum number of fish. Luckily, this is the special case where f only has one critical value on its entire domain. This critical value separates the domain into exactly 2 intervals. Since f prime is positive for the first portion of the domain, we know that f itself will be increasing for the first portion of the domain. Since f prime is negative for the remainder of the domain, we know that f itself will be decreasing for the remainder of the domain. Therefore, at the critical value, f has an absolute max, not just a relative max. We have accounted for the entire domain. So we say f of t has an absolute maximum at t equals 6.2035 because f prime of t is positive from 0 to 6.2035 and f prime is negative on the interval from 6.2035 to 8. So the maximum number of fish in the lake occurs at t equals 6.2035 hours. Let me go back for a minute. I skipped an important step. It's easy to forget when we use a graphing calculator to find a critical value, but we must identify critical values in our work like this. F prime at t is equal to 0 at t equals 6.2035. In the College Board rubrics, this statement is often worth a point all by itself, so make sure you don't skip it. There's nothing wrong with defining a new function f of t for the number of fish in the lake, and then using f of t and f prime of t in your justification. But I want to show you how you can do the problem without doing that. I mean, if you look at the College Board answer, they're not going to have a new made-up function for the number of fish. Since f of t is the number of fish in the lake, instead of mentioning f of t in the justification, we can just say the number of fish has an absolute maximum. Also, f prime of t is just e of t minus L of t. So everywhere we wrote f prime of t in our justification or in our work, we can just replace that with the expression e of t minus L of t. For the critical value, instead of saying f prime of t equals 0 at t equals 6.2035, we say e of t minus L of t equals 0 at t equals 6.2035. And in our justification, we say the number of fish in the lake has an absolute maximum at t equals 6.2035 because e of t minus L of t is positive from 0 to 6.2035, and e of t minus L of t is negative on the interval from 6.2035 to 8. This is what the answer would look like on the College Board answer key, so this is probably the safest way to go. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.